Question 8 now. It says, consider this initial rate data at a certain temperature for the reaction described by, so initial rate data at certain temperature for this reaction. Okay, we have N2O3 gas is equal, well, turns into NO gas plus NO2 gas. Okay, and then we're given this table, which is actually very crucial to answer this question. We have now the concentration, the initial concentration of each of N2O3 in different, well, we have N2O3 in different concentrations, and and here they give us the rate of the reaction based on the different concentrations. Okay, so N2O3, C is what is that? So that's exactly at the beginning, so they have 0 and exactly want the concentration of it, and then we have initial rate. Okay, alright, so now we have 0.100, 0.200, 0.300, okay, and we have 0.630, 1.260, and 1.890. So now that we've written that out, determine the value and units for the rate constant. So for this, what the question is asking really is, what is the relationship between increasing the initial concentration and the change in the initial rate, to find out how the rate law works. So for this, to find out actually the ratio, what we do is we take one concentration. Actually, we perform ratios here, but point being is that we do 0.100, that concentration had 0.630 of a rate, and 0.200 concentration had 1.260 of the rate. Okay, so if we did some moving about here, okay, well, actually we don't need to move anything actually. If we just divided by each one, we get that these two equal each other actually, because when we divide this, exactly, this is just double. This right here is 2 times what happened here, although they're the same thing. Point being, actually, let me actually rearrange this to where it makes more sense. Let me put it this way. When this was doubled, okay, this was also doubled. Okay, so 1 led to that and 2 led to that. Okay, so this is just 1 times and 2 times. So right here you can kind of say that this is going to be, you know, it's a one-to-one relationship, but we want to make sure that applies to everything going forward. So this is the 1 to 3 jump. Okay, okay, so we have 0.100 and 0.300. okay, and we now have 1.890 and 0.630. okay, and if you actually put this in your calculator, you see that this is actually now 3 times. Oops, 2 times here, 3 times, so there's the relationship here. Okay, so with that being said, now if you drew a pseudo graph, right, it will kind of look like this: 1, and then when it was doubled, 2, and was, you know, tripled from the 1, 3. and you have kind of a straight line. Okay, oops, let me just draw like that. All right, so with that being said, this is a linear relationship, not an exponential relationship. So that means that the rate is going to be to the power of 1, because the power of 1 is what implies a linear relationship. So really, you have rate k is equal to the concentration of N2O3 to the power of 1. Well, actually, sorry, it's going to be rate, I believe there's something before that, something times a rate is equal to that, but let's see here, there we go, yes. So rate is equal to k and 203 1. Okay, and the reason why we figured out 1, well, m equals 1, is because of this relationship here that we established. Every time we went up by a certain amount, the rate went up by that same amount as well. There's no like exponential growth or even logarithmic growth or anything like that. It was just 1 to 1. Okay, so let's see here. Yep, they show here that it was a 1 to 1. So the first order, and exactly. But they do go forward in terms of establishing what the actual rate is. Well, I mean the k. Let me see if the question is asking that. I'll determine the value and the units of the rate constant. So they do actually ask for that k. So the way they solve it there, actually, as you can see here, you can actually use, not even establish a relationship, and you notice m is equal to 1. You use any of the values there to find out what k is equal to. So we have the initial rate, so let's just actually use a 1.260 is equal to k times the concentration of N2O3, which was 0.200 at that time, okay, to the power of 1. And we know if it's to the power of 1, it's just 0.200. So now we divide both sides by that number. Okay. And let's see what we get. 1.2. We get that k is equal to 6.3. Okay, but now there's actual units. Okay, that's the part you can't forget. And because we know it's a first order reaction, okay, this is a part you kind of have to memorize, unfortunately, because each 0th order, first order, and second order each have different units for their constant. But for the first order, it's just going to be s minus 1. That is what we get for the constant here, the rate constant. Okay, so with that being said, let's see what else we can do here. How do we do? Yep, 6.3 negative second, well, the inverse of seconds. That is all correct. So with that being said, this is indeed correct, and this is how you solve question 8 here. Let me just make sure we go over everything. Exactly, we did establish the relationship. We know it's linear, so it's first order. And then with that being said, using that, we found out that the k value is 6.3 s to the minus 1, seconds to the minus 1. So let's go on to question